Normally, stars are born from gigantic clouds, collections of thousands or millions of solar masses of mostly hydrogen. In these clouds, matter starts to accumulate around the densest spots inside. As these spots get denser, their gravitational pull intensifies and they grow faster. Eventually, they generate so much heat and pressure that they ignite fusion reactions and a new star is born. But this puts a limit on their size. Nuclear fusion releases enough radiation energy that the surrounding gas cloud is blown away. The new baby star can't gather more mass. From now on, the star is living on the edge between two forces: gravity pulling in, trying to squash the star, and radiation created by fusion pushing outwards, trying to blow the star apart. So let's move on. Main sequence stars. Once large gas balls pass a certain mass threshold, their cores become hot and dense enough to ignite. Hydrogen is fused to helium in their cores, releasing tremendous amounts of energy. Stars that do that are called main sequence stars. The more massive a main sequence star is, the hotter and brighter it burns, and the shorter its life is. Once the hydrogen burning phase is over, stars grow up to hundreds of thousands of times their original size. But these giant phases only last for a fraction of their lifespan. So we'll be comparing stars at drastically different stages in their lives. This doesn't make them less impressive, but maybe it's good to keep in mind that we'll be comparing babies to adults. Now, red giants. When main sequence stars begin to exhaust the hydrogen in their core, it contracts, making it hotter and denser. This leads to hotter and faster fusion, which pushes back against gravity and makes the outer layers swell in a giant phase. And these stars become truly giant indeed. For example, Gacrux. Only 30% more massive than the Sun, it has swollen to about 84 times its radius. Still, when the Sun enters the last stage of its life, it will swell and become even bigger, 200 times its current radius. In this final phase of its life, it will swallow the inner planets. And if you think that's impressive, let's finally introduce the largest stars in the universe, hypergiants. Hypergiants are the giant phase of the most massive stars in the universe. They have an enormous surface area that can radiate an insane amount of light. Being so large, they're basically blowing themselves apart, as gravity at the surface is too weak to hold on to the hot mass which is lifted away in powerful stellar winds. Pit-sized stars like our Sun are more interesting. Imagine the Sun as a huge pressure cooker that fuses hydrogen into helium in its core through its gravity. The fusion of elements releases extreme amounts of energy that pushes outwards and stabilizes the star, keeping it in a delicate balance. When the Sun is old, the hydrogen in the core is exhausted, and the Sun will begin to burn helium into heavier elements. While doing so, it will shed its outer layers. When this process is over, more than half of the Sun's mass will be lost into space as a spectacular planetary nebula millions of kilometers across. What remains will be its former core. A white dwarf is born, a star corpse. While its former self was about 100 times its diameter, now it's only about as big as Earth, but still with about half of its former mass. This means it's extremely dense. A teaspoon of white dwarf is about as massive as a car. White dwarfs are very, very hot, up to 40 times hotter than our Sun, ranking among the hottest objects in the universe. But they are not incredibly active. All the heat inside of them is trapped and has nowhere to go. Only on its outer layer can it escape into space. But space is mostly empty, so heat can't be transferred by conduction. The only way energy can escape is by radiation. This is so inefficient that white dwarfs will take trillions of years to cool down, which may make them humanity's last refuge. They might be the last sources of light and energy in a dying universe. According to some estimates, white dwarfs might shine as long as 100 billion years, 10 billion times longer than the universe has existed. So far into the future that no regular stars will shine anymore. Galaxies will have evaporated. And only then will the first white dwarf turn into the first black dwarf. When this happens, the last hope for life will die off. Black dwarfs will be inactive spheres with no energy left to give. Still massive enough to kill you if you get too close. So cold that they'll be near the coldest possible temperature in the universe. So dark that they are practically invisible. In stars many times the mass of our Sun, things get interesting when the helium is exhausted. For a moment, the balance of pressure and radiation tips and gravity wins, squeezing the star tighter than before. The core burns hotter and faster, while the outer layers of the star swell by hundreds of times, fusing heavier and heavier elements. Carbon burns to neon in centuries, neon to oxygen in a year, oxygen to silicon in months, and silicon to iron in a day. And then, death. Iron is nuclear ash. It has no energy to give and cannot be fused. The fusion suddenly stops and the balance ends. Without the outward pressure from fusion, the core is crushed by the enormous weight of the star above it. What happens now is awesome and scary. Particles like electrons and protons really don't want to be near each other. But the pressure of the collapsing star is so great that electrons and protons fuse into neutrons, which then get squeezed together as tightly as in atomic nuclei. An iron ball the size of the Earth is squeezed into a ball of pure nuclear matter the size of a city. But not just the core, the whole star implodes, gravity pulling the outer layers in at 25% the speed of light. This implosion bounces off the iron core, producing a shock wave that explodes outwards and catapults the rest of the star into space. This is what we call a supernova explosion, and it will outshine entire galaxies. What remains of the star is now a neutron star. Its mass is around 1 million times the mass of the Earth, but compressed to an object about 25 kilometers wide. It's so dense that the mass of all living humans would fit into 1 cubic centimeter of neutron star matter. That's roughly 1 billion tons in a space the size of a sugar cube. Their surfaces reach 1 million degrees Celsius compared to a measly 6,000 degrees for our Sun. Okay, let's look inside a neutron star. Although these giant atomic nuclei are stars, in many ways they're also like planets with solid crusts over a liquid core. The crust is extremely hard. The outermost layers are made of iron left over from the supernova, squeezed together in a crystal lattice with a sea of electrons flowing through them. Going deeper, gravity squeezes nuclei closer together. We find fewer and fewer protons as most merge to neutrons, until we reach the base of the crust. Here, nuclei are squeezed together so hard that they start to touch. Protons and neutrons rearrange, making long cylinders or sheets, enormous nuclei with millions of protons and neutrons shaped like spaghetti and lasagna, which physicists call nuclear pasta. When neutron stars first collapse, they begin to spin very, very fast, like a ballerina pulling her arms in. Neutron stars are celestial ballerinas spinning many times per second. This creates pulses because their magnetic field creates a beam of radio waves which passes every time they spin. These radio pulsars are the best known type of neutron star, about 2,000 are known of in the Milky Way. These magnetic fields are the strongest in the universe, a quadrillion times stronger than Earth's after they're born. They're called magnetars until they calm down a little. From the outside, a neutron star is unbelievably extreme. Its gravity is the strongest outside black holes, and if it were any denser, it would become one. If you looked at a black hole, what you'd really be seeing is the event horizon. Anything that crosses the event horizon needs to be traveling faster than the speed of light to escape. In other words, it's impossible. So we just see a black sphere reflecting nothing. By the way, black holes do not suck things up like a vacuum cleaner. If we were to swap the Sun for an equally massive black hole, nothing much would change for Earth, except that we would freeze to death, of course. As powerful as black holes are, they will eventually evaporate through a process called Hawking radiation. To understand how this works, we have to look at empty space. Empty space is not really empty, but filled with virtual particles popping into existence and annihilating each other again. When this happens right on the edge of a black hole, one of the virtual particles will be drawn into the black hole and the other will escape and become a real particle. So the black hole is losing energy. This happens incredibly slowly at first and gets faster as the black hole becomes smaller. When it arrives at the mass of a large asteroid, it's radiating at room temperature. When it has the mass of a mountain, it radiates with about the heat of our sun, and in the last second of its life, the black hole radiates away with the energy of billions of nuclear bombs in a huge explosion. But this process is incredibly slow. The biggest black holes we know might take up to a googol years to evaporate. This is so long that when the last black hole radiates away, nobody will be around to witness it. The universe will enter its last stage, heat death, which will leave the universe unrecognizable. An absolutely dark and cold graveyard with black holes and black dwarfs scattered over trillions of light years. We don't know for sure what will happen with black dwarfs in the end. If the proton, one of the fundamental parts of atoms, has a limited lifespan, black dwarfs will slowly evaporate over many trillions of years. If the proton does not decay, black dwarfs will probably turn into spheres of pure iron via quantum tunneling over a time span so obscenely gigantic that calling it forever is okay. These iron spheres will then travel completely alone through a dark universe. Nothing new will happen anymore. Forever. While this may sound kind of dark, this is so far away that for our purposes today, it might as well not happen at all. It doesn't matter what happens in a billion trillion years. Right now, we happen to exist at an excellent time, able to be in awe about a universe filled with endless stars and light and planets, and enough time to visit them one day.